Okay, good morning, class. What I want you to do is take out the handout from yesterday again, the one that says Newton's third law of motion in sample problems. Yesterday we took up that question regarding Mike Camilleri of the Toronto Maple Leafs and Phil Kessel of the Toronto Maple Leafs. So what we're going to do this time is do a similar question just to see if you can get see if you can transfer those concepts over to different types of questions. And this time, if you can have a look at the first page, we have two steel blocks at rest on a frictionless horizontal surface. Block X has a mass of 6 kilograms, and it's attached by means of a light string to block Y of mass 12 kilograms. So we have a force of 36 newtons east, which is applied to block X, as shown below. And it says draw a free body diagram for each block. All right, so what I want to do in this case is take a look at take a look at the 12 kilogram block, and what I'm going to do is I'm going to draw a separate free body diagram of just that block. So what we're going to do is we're going to start off with a surface. The 12 kilogram block is just a box that looks like this with the center of mass over there. So what I'm going to do is I'm going to draw all the forces acting on this block. And I think most of you can see that right off the bat we do have a force of gravity acting straight down on this block. We also do have a normal force acting on the block like so. And if you take a look, there also seems to be, if you take a look at other forces acting on this block, it looks as if it's being pulled to the right by this 6 kilogram block. Now it's being pulled by the 6 kilogram block indirectly by the use of a string. Now since there's a string attached to the 12 kilogram block, strings of course apply forces of tension to that block. So what I'm going to do here is I'm going to label this force as my force due to tension. Okay? So if you take a look, those are all the forces acting on the block. One of the things that we're going to do, of course, is we're going to assume that there is no friction between the block and the surface. I know that because it's given in the question itself. All right, so very good. Now let's see if we can draw a separate free body diagram for the 6 kilogram block. So there's the surface once again. This time I'm going to draw the 6 kilogram block, maybe a little bit smaller because it's less massive. And let's draw the forces acting on the 6 kilogram block. Once again, I do have a force of gravity acting straight down. Once again, I do have a normal force acting straight up. Now, if you take a look at the 6 kilogram block, there is an applied force acting on that block. I'm going to label this as my applied force. And that applied force is actually 36 newtons to the right. Oh, sorry, not to the right, to the east, I should say. So there's a 36 Newton force acting towards the east. Now, if you look carefully, the 6 kilogram block also has a string attached to it. Now, that string, even though it's being used to pull on the 12 kilogram block forward, you know for a fact that from Newton's third law of motion that every action has an equal and opposite reaction force. So what that means is, even though the 6 kilogram block is pulling on the 12 kilogram block east with a force due to tension, well, there must be a reaction force. And in this case, the reaction force is that the 12 kilogram block is pulling back on the 6 kilogram block, in this case towards the west, with the exact same force of tension. So watch what I do in this case. I'm going to draw a force acting to the west on that 6 kilogram block, and that force is also going to be a force of tension. Now, if you look very carefully, you may notice that we have two forces of tension acting on the two blocks. These two forces of tension are actually the action-reaction forces. So if I could, maybe if I can zoom in here, this would be of course the action force. This one would be the reaction force. All right. Now, the reason why I'm doing this is because I know for a fact that if you take a look at my force due to tension, this one over here, it's being used to pull my 12 kilogram mass to the east. This force of tension is being used to pull my 6 kilogram block towards the west. So if you take a look at how I drew these forces of tension, you may notice that they're exactly the same magnitude. They have to be the same magnitude because Newton's third law states that for every action there's an equal reaction. Not just an equal reaction, but an equal and oppositely directed reaction as well. And you can see that both of these forces are in the exact opposite direction. Okay? Now, in the end, it doesn't matter what the value of this force of tension is going to be. It must have the same value as that force of tension. So let's see if I can let's see if I can solve this question now. One of the things I want you guys to understand here is that, well, if I go back to the above free body diagram, it does say that there is a frictionless surface. So if there's a frictionless surface, take a look at the entire diagram once again. So take a look at the big picture, if you will. Even though this 36 Newton force is acting on the 6 kilogram block alone, well, wait a second. Because the 6 kilogram block is also attached to the 12 kilogram block by the use of this string, it's almost as if this 36 Newton force is acting on the combination of those two blocks. All right? In other words, it's almost like saying that we have a 36 Newton force acting on an 18 kilogram mass. So if we do have a force acting upon a mass, then we should be able to solve the acceleration of the two blocks combined. So how do I do that? Well, I don't know if you guys remember this or not, but Newton had, of course, 3 laws, and if you go back to Newton's second law, his second law states that anything that accelerates has to be equal to some kind of a net force over mass. Okay, so in this particular instance, you can see that the only force acting on the two masses together, or at least in the above diagram, is 36 newtons towards the east. So I'm going to write that in here, 36 newtons towards the east, and it's acting on a combined mass of 18 kilograms. Okay. All right, so if I take a look at what we have so far, 36 newtons east divided by 18 kilograms, I should end up with 2.0 meters per second squared. And it's 2.0 meters per second squared also acting towards the east because, of course, we know for a fact that net forces and accelerations must always be in the same direction. So if you take a look at what I have so far, oops, let me just make this a little bit smaller. Okay, there we go. Oops. All right. So if you take a look at what I have so far, you can see that the acceleration of the entire system has to be 2 meters per second squared towards the east. Oops. Oh, sorry. One more time. Okay, wonderful. So both of these blocks combined have to be accelerating at a rate of 2 meters per second squared. Well, let's go back down to the free body diagrams that you drew. If you take a look at this free body, diagram here, it means that the 12 kilogram mass is accelerating at 2 meters per second squared, but it also means that the 6 kilogram mass is also accelerating at 2 meters per second squared. So if that's the case, let's take a look at the first free body diagram, and what I'm going to do in this case is I'm going to see if I can analyze this a little further. So let's just scroll back up here. And let me see if I can zoom. Whoop, there we go. Okay, so let's take a look at the 12 kilogram mass in a bit more detail. So I'm going to write down 12 kilogram mass. So if I take a look at the 12 kilogram mass, once again, we know that it's going to be accelerating. Therefore, let me just change the color of my marker here. Therefore, the acceleration of that mass has to be equal to some net force over mass. Well, we already know that the 12 kilogram mass is accelerating at 2.0 meters per second squared. And that has to be equal to some net force over mass. If I look at the free body diagram, I think most of you can see that, first of all, this normal force and this force of gravity must have the same magnitude since my block is staying level with the surface. It's not accelerating up and it's not accelerating down, which means that the only force contributing to the net force has to be this force of tension. So let's write down the force of tension as the net force. And all of that is acting on just that particular mass, which is 12 kilograms. So if I rearrange the equation and isolate for my force of tension, it should turn out to be, well, 12 times 2 works out to be 24 newtons. So the answer is 24 newtons, and since my answer is positive, it does happen to be 24 newtons towards the east, which makes a lot of sense because if I go back to the original free body diagram, I think all of you can see that this force is in fact acting towards the east. Okay? And that's what you should have for the 12 kilogram mass. Well, let's take a look now at the 6 kilogram mass. Now the 6 kilogram mass looks as if there's an extra force acting on it. There's the applied force, 36 newtons towards the east. So let's see if I can take a look at the 6 kilogram mass in a bit more detail. So let's write down 6 kilogram mass. And, oops. Now, we know for a fact that the 6 kilogram mass is also going to be accelerating at 2 meters per second squared, so we know that anything that accelerates must follow Newton's second law. So its acceleration, you just told me, was 2.0 meters per second squared. That's got to be equal to a net force over mass. Well, if I study the free body diagram, once again, these two forces, normal force and gravity, have to be balanced because, again, the block is not accelerating up or down. It's staying level with the surface. So the only two forces that are contributing to the net force in this case are the applied force towards the east and this force of tension towards the west. If we call east to be the positive direction and force of tension to be the negative direction, what I'm going to write down in this case is that the net force acting on the 6 kilogram mass is going to be due to my applied force, 36 newtons, and minus the force of tension. Why negative force of tension? Because force of tension is acting in the negative direction, which is towards the west. And all of this divided by its mass, which is only 6 kilograms. Okay, so if I rearrange this equation, I can see that 6 times 2 is 12. So I get 12 being equal to 36 minus force of tension. Rearrange the equation and isolate for force of tension, and what you end up with is force of tension being equal to 36 minus 12. Ooh, look at that. 36 minus 12. Well, that turns out to be 24 newtons. So 24 newtons all over again. Now, the answer in this case, or the magnitude of the force of tension, is of course 24 newtons. The direction of that 24 newtons, though, is, if you take a look at the diagram, since the vector arrow is pointing towards the west, it's got to be a negative value. So we accounted for that negative sign when we labeled this force of tension here to be negative. Okay, and just by labeling it as negative, we are saying that we already know that it is in the west direction, which means that this 24 newtons is towards the west. Thus, if you take a look at the two values of the force of tension that you just came up with, if you take a look at this 24 newtons that you came up with for the force of tension acting on the 12 kilogram mass, and if you take a look at this 24 newtons west acting on the 6 kilogram mass, they are in fact equal in magnitude. They are in fact in the opposite direction. Thus, in one sense, we've kind of proved Newton's third law to be true. Okay. In any case, hope that works, or hope that helps you guys out. What I want you guys to do for homework today is, if you guys can continue with oh geez, I forgot which bullet we were on. It was the bullet that deals with Newton's third law, and I think that was bullet number 4. So please, if you guys can check back with your unit outline, please finish off that particular bullet, and I'll be teaching a completely new thing tomorrow as well. So everyone have a good night, and I'll talk to you next week. Okay, thank you. Goodbye.